Hello, everyone. Welcome to this week's session. Hopefully, the majority of you will have seen those emails that I've been sending round and will have managed to get some form of access to SolidWorks, including the simulation side. So, the two options, if you still haven't been successful, is that you can set it up on your local machine. I've sent out some instructions that show you how to do that. It's known as the SEK version, which is the one that you need to set up. If you're having troubles with that and you can't overcome them, then there's always the virtual desktop, which you can get to through the main shoe homepage, which is here. And again, I've sent out a little guide with a video just to kind of show you how to get into that. There's a lot of guides already written in here, so I haven't kind of gone through that step by step. But certainly you can get access to SolidWorks via that route as well. And it will provide you with all the simulation side of SolidWorks that you need to actually run through these sessions as we do them. So if you still haven't done either one of those, then you'll have to just watch this session. I'm recording it, as I always do, and I'll upload the recording so you can work through it when you do get SolidWorks in some form, either locally on your machine or using the virtual desktop. So yeah, that's that bit covered. Back to what we're actually going to cover this week, which is in the learning materials. And we're going to make a start on this section here. So simulation and optimization. And the PDF that we're going to work through is this bottom one there. It should be at the top of the list, but I've just updated it. I've tweaked it slightly today and then re-uploaded it. So it's moved itself to the bottom of the list. But if you open that in a new tab, you can see we're kind of using the sort of screenshot method again. I've tried to minimize the amount of typing that I have to do and you have to read on these tutorials. So this coupled with what I'm going to show you live, and then obviously what you can dip back into in the session recording that I'm going to upload, you should be fine running through this either now or later on. So what is it that we're going to cover? We're going to kind of have a little play around with some of the simulation tools in SolidWorks, because undoubtedly when you're trying to design your parts or your entire design, your assembly, there tends to be at least some form of design constraint in terms of the amount of material that you might use. Whether that's for lightness of the actual design, there's some sort of functional reason that it needs to be quite light, as in parts for racing cars or aerospace or sports equipment. There's actually a functional reason that it needs to be light in those cases. Or in other industries, it's just trying to minimize the amount of material, the amount of raw material that you're going to require to actually manufacture your parts. So yeah, but undoubtedly you'll come across this constraint where you're looking to minimize the amount of material for whatever reason. But obviously going hand in hand with that, as you minimize the amount of material in any sort of design, the design tends to get inherently weaker. So it's always a balancing act between the two. Is it functionally strong enough to fulfill its function, whatever that may be, with the product that you're designing? Again, to relate it back to automotive, suspension arms and things like that, the lighter they are, the less unsprung mass you're going to have in the system, which is a good thing. But then obviously they have to withstand the sorts of forces that they're going to see in use. So yeah, what we're going to focus on here is tools within SolidWorks to allow you to analyze those sorts of things. So the masses of things, versus the sorts of stresses that parts are going to see in service, and then make sort of updates to your initial design to try and use that information that the system is giving you to optimize the design that you are creating. So it's that sort of workflow that we're going to kind of investigate in this session. So the first thing that we're going to do is just hopefully very quickly model up this simple part that you can see on my screen. So we're going to look at some of the tools in SolidWorks in this first section to allow you to analyze things to do with the mass of your design. So there's the mass itself, but there's things like center of gravity and those sorts of analysis tools that are available within SolidWorks. So what I'm going to do, we're just going to model it up from the images on the screen there. So if you want to get the PDF on your screen, you can do it that way. I'm going to push this PDF across onto my other screen, but you can follow along with me as I sort of model this part up. So I'm going to go new part, and this is just a simple 2 extrude part. There's an extrude that kind of makes the base of it, and then there's another extrude that kind of makes the top section. So I'm going to click on the front plane first, and then go to features and click on extrude boss base, because I want to begin an extrude boss base and I want to sketch on the front plane. So there we go. And then I'm just going to get the corner to corner rectangle tool. So corner rectangle, and I'm going to drop one corner on the origin and then drag the other corner kind of up there somewhere.
Sorry, which PDF was it?
Which PDF? It is that one there. Simulation, Evaluation and Optimization PDF.
Okay, thank you.
Yep, okay. Right, so the length of this rectangle needs to be 75 and the height needs to be 25. And then we can OK that sketch. And then it's going to be a mid-plane extrude because we want a nice plane sandwiched in the middle of this. And it's going to be 120 deep like that. So that's the first extruded feature. The next one we're also going to create on the front plane because we want it kind of centered around this one. So we're going to create this second extrude as a mid-plane extrude as well. So extruded boss base, which plane? Front plane again. And all I'm going to do for this extrude is one of those thin extrudes that we had a look at a few weeks ago where you just need to create, in this case, a single line. So I'm just going to sketch a single line in something like that. So you can see I've allowed it to add a coincident relation on this end, so it's kind of stuck to the top of the existing block. And then I'll put some dimensions on that as well. So I'll put an angular dimension between the line itself and that top plane down there. So that dimension, that needs to be 60 degrees, like that. And then the angular length of the line. So again, we kind of talked about this. If you place the dimension there, you get the length of the line along its length sort of aligned. If you put it there, you get the vertical length of the line. And likewise, if you place the dimension up there, you get the horizontal extent of the line. But it's the aligned dimension that we want. So we want it running parallel to the actual line itself. And that needs to be 350 for that one. And then one final one, which is back from the front edge or the left edge here of the box back to the beginning of our line there. Needs to be 20. So I'll just zoom back out so you can see that. Is that correct? Yeah, I think that's correct. So that's what we should have. So there's a 20 down there, just defining where that first point of the line sits relative to our original. And then when you get that sketch, as it is on my screen there, if you click on OK, and then because we've just provided it with a single line, which isn't a closed boundary of edges, the system's activated that thin feature option again. So it just adds a certain thickness of material onto either one side of the line or the other. And in this case, we want the material, as I've got it, kind of going downwards and to the right. So it's on the right-hand side of our diagonal line there. Because that means it's going to intersect with that box there. So when we finally OK this second feature, it's going to merge itself into that first body that we created with that first feature. So I just need to change some of the options about it first. So the depth of it needs to be 100, so it's not quite as deep as the first feature, but we want it as a mid-plane extrusion. So something like that. That's what you should be looking at. And then we can OK that. So then it's unified those two into a single unified solid body. So on mine, or on my installation, you can see I've got the solid bodies folder there. It's merged them together. They're a single block of material. And in this example, that's significant because we're going to tell the system that our part has a density. So we're going to dip into the material library that's stored within the system. We're going to set this part as a particular material, and then all the properties of that material are going to get applied to that part as a whole. Whereas if these two features hadn't been merged together, we would have to apply the material to one of them and then maybe apply the same material to the other one, or possibly a different material depending on what our design sort of required. But we don't have to care about that because we've just got a single solid body at the moment. So I'll move down the PDF a little bit. So we've created the simple model. I think I forgot something there. The thickness of the thin value there, thin feature, should have been 12 mil. And I think I left it on the default 10 mil. So I'm just going to drop back into that second extruded feature. So I'll click on it in the feature manager, click on edit feature, and it'll drop me back into the setup dialog for that feature. And then that option there, which is currently set on 10 mil, I want to set that to 12. And then when you press enter, you should see the yellow preview kind of update slightly, just to reflect that. So then I'll OK that. And I'll bring the PDF back. Was that just in the chat, just for a second? Is that the same person asking about the PDF that actually asked verbally?
Yeah, that was me.
I'm just checking that everyone's got that PDF. So what we're going to do next, as I kind of said there, was we're going to dip into the catalog of materials that comes with SolidWorks as standard. So all these materials have got various properties to do with them stored within this library, and we're going to have a little look at that now. So on the feature manager where it says material not specified, if you right click on there and go to edit material, just before I do that, you can see you've got a few kind of favorites here. So there's a favorites list of materials that you can add to, and you can see there's an option saying manage favorites. These are the default favorites. So these are the ones that the people who sort of sell SolidWorks have assumed people are going to reuse time and time and time again. So if I wanted to apply just one of these to my model, I could just click on it here. And as I say, you can add to that favorites list. You can delete things off there if you never use them. But what we're going to do, we're going to drop into the entire library so that we can see all the materials that are stored within SolidWorks' material library. And the way that you do that is edit material. And then the menu that you should be looking at should look something like this. So I'm just resizing it a bit. And then I'll minimize that steel folder. And you can see there's various classes of materials in here. There's lots and lots of metals, because these sorts of stress analyses are kind of most relevant for metals. Their sort of validity of these kind of FEA style tools is kind of more questionable when you start using them on things such as woods or rubber or plastics. Carbon fiber, there's been big strides in creating FEA systems that deal with carbon fiber quite well. But again, these are primarily grown out of the analysis of metals. So we're going to stick with metals, and we're going to apply a steel to this design. And I think the one that I've said that we're going to use is a nice, easy one. It's the one at the top of the list there. So 1023 carbon sheet steel is what we're going to apply. And just before I do click on apply, you can kind of browse the properties that are stored within the system to do with this material. So you can see we've got the yield strength, we've got the Young's modulus or the elastic modulus, we've got the density, which is kind of the one that we're interested in for this example. Now, not all of the materials in the entire library have all of the properties filled in. You can see I picked something way at the other extreme, which is a balsa wood. So you couldn't really get further away from steel that we were just about to select. And you can see a lot of tensile strength. Yeah, it's questionable. It depends a lot on the, I don't know, the tree that you got the wood from. So yeah, it's worth checking that the material that you're trying to analyze actually has the relevant values entered into its actual entry within the library. If not, you can create your own materials. And you can obviously look up the missing values and fill them in manually yourself. We're not going to cover that particular skill in this tutorial, but just know that it is there if you need it. And if you can go away and research whatever material it is that you're going to use, you can create a sort of digital duplicate of that material within this material library. But for the time being, I think we'll just apply that carbon steel, 1023 carbon steel from the top of the table there. Click on apply, and then it may not have been obvious because I had this window blocking out my part, but it's a small thing, but the actual appearance of the part actually changes when you click on apply as well. So this part now on my system has sort of a slightly sort of brownish hue to it, whereas it used to be just plain grey. Not that significant for what we're doing, but if you spend a lot of time setting up the appearances of your models and then you come to apply a material, it will just dump all those fancy colors or fancy finishes that you've set. Maybe you were creating a rendered output of your part for some sort of products catalog, and just be aware when you apply a material, it kind of overwrites the appearance. So yeah, I've applied that. So I'm going to close that catalog down, that material library down after I've clicked on apply. I can check that it has been applied, other than the fact that the appearance of my part has actually changed slightly. You can see there the material that's been applied to it is now actually shown, where previously it said non-applied, I think. So the next bit that we're going to do, we're going to just assess the overall mass of our part, and then a little bit later where the center of gravity of this part is kind of located, because that's kind of the focus of this first tutorial, is modifying our design and seeing how that affects where the center of gravity is, or the center of mass. So the way that we do that is in the Evaluate tab. So all the tools that you would want to use, well, to evaluate your design, including measuring distances or having a readout of things to do with the mass, such as center of gravity or the mass itself or the total volume of the part you can get in there as well, up to quite complicated things such as these tools over here. They put what's known as zebra stripes on the part. Now, they're pretty useless for this part that we've created because it's all flat faces. But if you design parts which are, let's say, flowing body panels, and maybe you want to check out the aesthetics of them and see how one section of panel flows into the next one, and see whether they've got a crease where you intend the crease to be, or whether there's a harsh edge where you intended it to be smooth, then tools like this, where you are sort of analyzing the curvature of a part, become quite useful. But again, we're not going to really use those ones. We're using more of the sort of engineering tools, the mass tools, the measurement tools, and then later on some of the stress analysis ones. But yeah, it's good to know that they're there as well. And there's things to do with thickness analysis, and you can analyze the finished surface within a design and make changes to it if that's too thin. But what we're going to do is use the mass properties option over to the left there. And then what happens is you get this readout with all the things related to the mass properties of the part. As I've already said, there's density of the material that you've applied. There's the overall mass of the current design that you've got in the design window there. There's the current volume of it as well, in whatever units you've set the system up with. Now mine's in cubic mil. If I want to change those units, I can. Where is that? Yep. In options there, you can use the default or you can choose your own units. So if I want it in meters and meters cubed, I can change that in there. Yeah, there's the option to change that. The thing that we're really interested in is this little coordinate system that's appeared there, because that represents the center of gravity of this particular design. So it's a simple kind of design criteria for certain functional parts that they don't fall over under their own weight. So the thought is that this is some kind of part that has to balance, that has to sit on this bottom face here on a flat level surface. And an easy way to assess using this tool if the thing is going to fall over or not is the center of gravity outside of the footprint? And currently it is on the x-axis. Now we don't know how much just from this readout here. We could kind of figure it out because the center of mass is listed there, but that's with respect to the part origin itself. So if I just momentarily shut that down, there's the part origin. So the horizontal distance, or the distance in x from the part origin, was listed there. So we could kind of calculate that and say, well, how long did we make our base? Oh, it's 75. So if we're up above 75 in x, this thing's going to fall over under its own weight. But we're going to do all that, but a slightly more kind of automated version of it, rather than sort of calculating ourselves. And the way that we do that is tick that option there, create center of mass feature. And what that does, when I exit this mass properties menu, there will be a new point created on the model there that represents the position of the center of mass, or the center of gravity for the part. And what I can then do is I can use some other tools up here, primarily the measure tool, to actually get the distance between that final face of my base and the center of mass. So I'm kind of using the tools within the system to give me the reading that I want. So make sure you've clicked on create center of mass feature, then shut this menu down. You can just click on the X at the top of the menu. And then if you're not seeing a little icon there, like I am, it's because the center of mass features are being hidden on your system. So in the same way that we can hide and show the base planes, like that, or any other type of feature, you can hide and show centers of mass as well. So when you click off it, if it disappears, chances are you've got it unselected there. So you need to make sure that that option in the hide and show menu is selected, and then it will always appear on your graphics window. So the next thing that we're going to do is we're going to create what's known as a sensor to measure the distance, or monitor the distance, between that upright face there and that center of mass feature. And more specifically, not the distance kind of in a straight line from one to the other, because that's kind of a diagonal line. We want the distance along the x-axis only, because that's all we're interested in. We're trying to ultimately modify our design in a certain way that brings that center of mass back within the footprint of the actual part. So let's do that next. So I just deselected everything there just to make sure that I'm not inadvertently sort of pre-selecting any geometry. So the way that I did that, you can either hit escape a couple of times or just click in some empty space to make sure you've not selected anything. And then I'm going to use the measure tool. So you can see this tool's really useful because I keep a copy of it in my sort of quick access toolbar there. I keep a copy of the mass properties and I keep a copy of the measure tool. I've actually got two because I was illustrating it to another group, or maybe you, that you could add icons into that actual menu bar. So select the measure tool. You get a new readout window here. This entry box is highlighted in blue, which we've kind of encountered before. When an entry box like that is highlighted in blue, the system's waiting for you to click on something from the model. And in this case, we're going to click on that face and that center of mass feature. And what you get instantly is a readout telling you kind of four main pieces of information. Normally, there's the shortest distance between the two objects, which is this number there. Could you show us how to put the measure tool in the toolbar quickly? Yeah, no probs, no probs. So let's just have a little aside where we kind of customize this head-up toolbar again. So you'll have some icons there already. Just right-click on any one of them. It doesn't have to be one specifically, just any of them. So right-click, go down to Customize. Then this menu should pop up. And then the tab that you want is this one, the Commands tab at the top. So here's all the different icons in the system, all arranged into little kind of subcategories. So as you click down through all of these, you'll see the icons available on the right changing. So it's just a case of finding the area or the category that's got the measurement tool in. And it should be in, I think it's in, you would think it would be in Evaluate to match the tab up here, but it's not. It's in Tools. So if you go down to Tools, the Measurement tool and the Mass Properties tool are both in there. And the way that you put them in the toolbar is you just click and hold here and just drag them up to the toolbar. Then just let go. And they'll get dropped wherever you let go. So yeah, and then if you want to reverse the thing, you can grab things from the toolbar there and drag it back into the kind of buttons area here, and it will actually get rid of them again. So yeah, really simple. And if you've got your own installation of SolidWorks, I would recommend you start doing that. If there's a tool that you keep going to time and time and time again, you can add it in there just so it's a bit easier. You can see I've added some others in. Some to do with deviation analysis, assembly, interference detection is quite a useful one as well. And I think that save all is a new one, maybe that I've added in. I forget what the default looks like. But yeah, everything within the system is available there, so you can kind of browse through and find things that are useful and then put them up in that toolbar. If you want the save one in there, that's in the standard subsection. So if you go to standard, that's the save icon. And I just put that there just to encourage me to save it more often, because obviously it's going to crash occasionally. Any system crashes every now and again. So if you've got the save option right there, sort of encourages you to save more regularly. So yeah, that's that. When you're finished with that menu, you can just click on OK and it will disappear. So back to what we were doing. So let's get the measure tool again. I'll use my measure tool that I've just put up there just to prove that it works. And then it's that rear face that we want to click on. You can see it's entered in that entry box in blue and that center of mass feature. And yeah, to get back to what we're looking at, so there's actually 5 different numbers here. So there's the normal distance. Now that only appears because I've clicked on a planar face. So what that does is it takes that planar face as an input and it says, Yeah, it's a planar face or a flat face. Therefore, it has a normal direction. And we've kind of covered this. Normal means at 90 degrees to. So if you imagine an arrow coming out of that face at 90 degrees to the face itself, that's the normal direction. So you can see if I zoom in a bit, the normal distance is indicated in purple here, and you can hopefully see there's a little line indicating its direction there. So that's the normal distance. But that kind of only applies to faces or edges that are straight. You get a normal distance readout. There's the distance in x, and obviously this is with respect to our kind of base coordinate system. You can see it down at the left of the graphics window there. So there's a distance in x, there's a distance in y, and then there isn't a distance in z, because the center point of my face is coincident with the center of gravity, because this is a part that's symmetrical about a kind of center plane. So you can see I do get a readout on z here, but it reads as 0. So it's not actually shown in the graphics window with a little kind of call out like we've got here. And as I've already said, the one that we're interested in is the distance on x. We're looking ultimately to modify our failing design, because our design kind of fails the piece of design criteria that I said right at the top, which is I want it to sit on a level flat surface and not fall over under its own weight. So currently I can be pretty sure that it is going to fall over, because that normal distance, if I just rotate my view round to the side quickly, yeah, I can kind of see that that center of mass is hanging out beyond that face. I don't really need the readout to tell me that, although it is useful. You can see that there. So what I'm looking to do, make some design changes, bring that center of mass back inside the footprint of the base again. So what we could do is use this measurement tool, clock that the measurement is hanging out too far over the base, then close this measurement tool down, make a change. In this tutorial, I've said that the only change that we're allowed to make with this design is that we're allowed to increase this thickness value of the base. So we're allowed to increase the mass of the base of this design by increasing its thickness. But this is a little bit long-winded, because what we'd have to do is change this value. So let's, for example, change it to 30, do a rebuild. So I'll click on the rebuild icon at the top there. The thing will rebuild, and then I'll have to get the measurement tool out again, go through the same kind of long-winded process again. Yeah, we made it slightly better there, but it's still kind of beyond the base. You get the idea. That's kind of the very labor-intensive way of doing it. The alternative is, once we get the measurement tool active and we click on the two things that we want to measure between, we can click on that icon there. And what that does, well, it does what the icon says. It creates what's known as a sensor. And the sensor basically sits in the feature tree up here in the sensors folder, which you may not see on your systems until you create a sensor. I've got mine so it's visible all the time. And any one of these values, so the normal distance, the x distance, the y distance, the straight line distance between them, I can log in this sensor. So in our case, we're going to log the x distance. And it just gives you a nice little readout in the feature tree there that you can keep an eye on. You don't need to keep opening this measurement tool up and assessing what effect your design change has just had. You can just kind of glance at it over there, and there will be a little readout telling you what it currently is. So that's what we're going to do. So click on Create Sensor, which is that icon that looks a bit like a graph, because that's kind of the intention. The intention of these sensors is to monitor changes to your design and what effect they're having. And then we've got a bit of setup to do here. Which value do we want to monitor of those 5 values? We want to monitor either the normal distance would be acceptable, or the distance in x, because they're both the same in this particular instance. So delta in x, I'll select, and then click on OK. And then if I open up the sensors folder, you can see it's monitored in there. So now when we make a change, we won't have to do the measurement tool and click on the faces again. It'll just keep track of it. So if you double click on the base feature like that, let's bump it up to 35 mil. So I just double clicked on the height there, which in mine I've already set to 30. Yours might still be on 25. Change it to 35, and then if we're having a good day, we should be able to click on the rebuild icon there. So regenerate. Yeah, mine worked. So you saw that get a little bit thicker. Click on OK, and then I have to go back to my feature manager there. So we were in that tab, and I clicked back on feature manager. Yeah, I've minimized it even more. So it's coming down. It's gone down to 5 now. So it's only overhanging by 5. Now, this is by no means a perfect tool for this experiment, because what's going to happen if we keep going down in small increments like we are doing, say 5 mil, we're going to get to a point where it's going to cross 0 and the center of gravity is going to be within the base. And then as we increase the thickness, then it's going to get, this value is going to seem to increase again. But what it's going to do is it's going to get further away from that face there, but it's now traveling towards the center of the base. So we're going to have to be a little bit sort of aware that that's going to happen. So let's increase the thickness again. Let's go up to 40 this time, and then we'll do a rebuild. So you saw the base increase slightly. Go back to my feature manager tab. So there's the feature manager tab. Yeah, it's come down again. I still think we're outside the base. Yeah. So let's do 45. So we're just kind of inching our way up. Check it again. Yeah, we could have transitioned to being within the base now. So this is where we've got to be a little bit kind of investigative, let's say. So let's go slightly up. Let's go up to something like 48 and see what happens. So I'm going to click on the green tick now. And then I'm going to do a rebuild to increase that. I suspect we're within the base now. So I'm going to do a bit more investigation. What I'm going to do, I'm going to look at my part side on like that. And I'm going to get the measurement tool again and try and replicate what I did before. See if I can spot whether I'm inside or outside the base. I'm inside now. And the way I know that is that green line which has been drawn. So you can see there's a green line and there's a black line there. The green line runs vertically, perfectly vertical on the y-axis. So if I zoom in, I know that the lower point of that green line is touching that face on my base. And I can see that the center of gravity is off to the left of it. So I know now that the center of gravity has come within the base. So I've kind of achieved what I set out to achieve. Although in this particular sort of design brief, the kind of only driving force that I kind of put behind it was that you just bring the center of gravity within the base. What I should have said was you need to bring it within the base, but you need to leave it as close as possible to unbalancing the part. So, because you could have brought it within the base by just increasing the thickness of the base to a meter thick, and that would have achieved that one design goal. But in reality, when you get some sort of design brief, there's competing goals or competing things that you're trying to achieve, and it's balancing them all against each other. That's kind of the skill, if you like. So let's imagine that for this example, we're trying to get that center of gravity, yes, within the base, which we have achieved, but as close as possible to unbalancing the part, which I would say is purely an interpretive kind of outcome. But I would say within 0.2 of a mil of unbalancing it, we've kind of achieved that. So yeah, that's a simple kind of introduction to using some of the evaluation tools within SolidWorks to kind of drive your decision making within your actual designs themselves. And this is kind of another good thing that this sort of simple intro to it kind of illustrates to you, is that it's an iterative process. Undoubtedly, you'll get some results, be they just a number like this or an actual stress plot, which is what we're going to look at next. So I'm just furiously fast forwarding through the PDF. So this is the sort of thing that we're going to output next on a different part. But either way, whether it's just a simple number or whether it's a nice plot like this, you're taking that information, that output from your analysis, and you're feeding it back into the design. And you're possibly making a change to the design and then running the analysis again and then seeing how that affects the outcome of the analysis. And then maybe again come back and then rerun everything again. So it's this circular kind of iterative, change something, run the experiment, look at the results of the experiment, use that to make some kind of wise decisions about the design, and then run the experiment again, and so on and so on and so on, which is kind of sort of described in the term optimization, which is kind of one of the things that I said we were going to look at within this tutorial session. So you can save that or you can dump that part. It's up to you. If you want to save it, you can. I think I'll probably just minimize mine so I can refer back to it at some point if we need it. But what we're going to look at next is using the more full-blown kind of simulation tools. So we're going to ultimately generate those stress plots that I've just shown you. We're going to do it on a very simple example, or maybe simple is the wrong word, a very common example, which is an I-beam, which you would obviously use in kind of structural engineering of buildings and various civil engineering projects. But it's a common component that gets reused time and time and time again in various industries. And it's a nice example for us to kind of play around with. So that's the kind of initial cross-sectional size and shape that we're going to create. And again, I'll just drag that onto my other screen and then drop into creating a new part and click on extrude boss base because it's just a simple extrude again. I think we'll sketch it on the front plane, and then I'll show you a trick just for speeding up this sketching. So the I-beam has two lines of symmetry, or its cross-section at least has two lines of symmetry. So what I could do, and don't do this as I do it, this is just an example of possibly one way of doing it. I could sketch that shape, and then I could mirror it once about that vertical plane, and then I could select both of the shapes then and mirror them again about that horizontal plane. And that's a perfectly valid way of doing it. But let me show you a little sort of time-saving tool that at least removes one of those steps or kind of automates it slightly. So dynamic mirror entities. So you want to click on that option, and then I'm going to click on the vertical plane. And then I'm going to get my line tool, and hopefully you'll see what happens as I start sketching. So it's dynamically or on the fly mirroring whatever I do on the right hand side there over to the left hand side. So that's a nice kind of little trick that you can use rather than sketching everything and then saying to the system, right, I'd like to mirror all this geometry now over to another portion of the sketch. You can actually do it on the fly. And then I'll hit escape because I don't want the line tool anymore. Unfortunately, then I've got to select all that geometry. So I'll do a box select like that, and then do a normal mirror. So mirror all those entities. Because I pre-selected them, they're all listed in that blue box there. All I then have to do is tell the system what I want to mirror them about. So click on mirror about, horizontal plane, and then click on the right mouse button. You haven't got that feature. I was sure I hadn't put that in my toolbar, but maybe I have. Okay. I mean, I can show you how to add icons up there as well if you want. It's in tools. It is. So there's a wider selection of sketch tools, and they're all available in that tools menu, sketch tools there. And that kind of applies for features as well. So within the features tab, these are kind of the more common features, and I've kind of customized my menu there and added some other ones in that I find useful. In a similar way that we customized this quick access toolbar, you can do the same for all these menus or these ribbons across the top. So the sketch menu, the features menu, all of them. So yeah, dynamic mirror entities, if you wanted to use that, you could either right click and go to customize. Is it customize? Yes, it's customize again. Go to commands, go down to sketch, and there's a whole host of sketch commands there that you can just drag and drop them onto the toolbar at the top. So yeah, it's really customizable, SolidWorks these days, and it's quite easy. The way that you do it, it tends to be the same whether you're adding icons to this quick access toolbar or whether you're adding them into the main kind of ribbons at the top of the screen, the main sketching menu or features menu. But yeah, you don't need to use the dynamic mirror. That was kind of a time-saving tool that I was just kind of illustrating. You could use the two mirror commands that I kind of talked about to begin with. So just to illustrate that, let me delete everything. And then I'd just use the line tool and I'd sketch a quarter. Oh, I've still got dynamic mirror switched on. Apologies. Let me switch that off now. So sketch a quarter of the I-beam shape, something like that. Press escape because you don't need the line tool anymore. Click on the standard mirror entities. What do I want to mirror? So the entities to mirror. Just do a box select around all of that. What do I want to mirror about? So click on that box to activate it. I'll mirror these initially about the top plane there, and then right click to OK that mirror command, and then just run the mirror command a second time. So mirror entities, entities to mirror, do a box select on everything this time. Mirror about what? I want to mirror it about that vertical plane, that right hand plane. And then again, I can OK this mirror command by right clicking the right mouse button or right clicking the mouse. And you can see that there just by my pointer, there's a mouse with a little green tick on the right button. So yeah, that OKs that. Anyway, however you get to that final shape, what you want is a shape that is linked. So the four quadrants of it are linked together, because otherwise what you're going to have to do is you're going to have to put more dimensions on it than you should. So what we want to do, for example, is specify the thickness of kind of that bit of the I-beam as 15 mil, but we don't want to then have to specify the thickness of this bit of the I-beam as 15 mil as well. We want them to kind of stretch and scale together with each other. So that's why we use the mirror command for that. So when you do get to that point, so you've either done the two mirrors or you've done the dynamic mirror and then one manual mirror, smart dimension, that edge there needs to be 10 mil. That edge there needs to be 100. And the overall height of the entire I-beam shape needs to be 150. And then the thickness of the web section in the middle, which is that kind of joining piece between the two, the top and the bottom, is 10 mil. And when you do that, it should, all the edges should have turned from blue to black, because they're all kind of locked in position now, either through those symmetric relations that have been put in when we did the mirror commands, or the dimensions. So I'm going to click on OK. And then I think the depth or the amount of extrusion is 2,500. So again, this is a neat point where we can just illustrate that even though I'm working in millimeters, if I type 2.5 m, the system understands that. It understands that I'm typing in meters now because I've put that m after it. And if I press enter now, it converts it into millimeters for me. So if you've got a huge number, I suppose the ultimate expression would be if you've got several kilometer measurement, you could just type km after it and it will convert it into whatever units your part's actually using, which is quite nice. And then again, we'll go mid plane just so that we've got a base plane in the center of our extrusion. So that's kind of the shape that we're beginning with. It's just a standard I-beam shape. I think I even got it out of a I-beam catalog. So the height to width and the thickness of all the webs and the ends it's real. There is actually an I-beam that you can purchase that's this size and shape. And what we're going to do is, I think what I'm going to do initially, I'm going to deviate from what the PDF's telling us to do, and then we're going to loop back and perform these next few steps in a second. Because what I want to do is I want to set up the kind of simplest simulation that we possibly can of this. And then we'll look at the failings of that simulation that we've set up. Not the failure of the part, but our failings as in we've not put enough thought into the setup of it. But it's good to look at these things because it kind of avoids making these sorts of mistakes again. So we need to drop into simulation. So on my system, I don't have a tab at the top there yet that is simply marked simulation. I have flow simulation over here, but that's not what we need. So you may have one already if you've run that SEK version of SolidWorks. But for me, I have to go into SolidWorks add-ins and then, simulation is switched on. Can I just not spot it? Let's try that again. So I'm just turning simulation off and then turning it back on again in the hope that the tab will actually appear. There it is. It's popped up. I don't know why it wasn't visible before. It should have been because I had it switched on. But that's how to turn the simulation add-in within SolidWorks on or off. Or for that matter, any of the other add-ins that you may or may not have access to. And the reason that you might turn one of them off or some of them off is it makes the boot up of SolidWorks run quicker if you have them switched off. So if you don't use them very regularly, I recommend that you leave them switched off most of the time. Because it's no big thing if you only use them very rarely to just come in here and switch on the one that you need at any given point. If you have them all switched on, SolidWorks can take an age to actually boot up. So, yeah, you kind of know that now. So if we click on the simulation tab, there's only kind of one icon available to us. So we just want to click on New Study. I don't want to click on the drop down there. I don't want advice on my new study. I just want to click on the actual icon itself. New Study. We're just going to run what I would regard as the sort of standard study type, static study. So we're not going to change anything in this menu. We could name this study if we wanted. Again, I'm not going to in this particular example. So I'm just going to click on the green tick. Then we drop into the SolidWorks simulation manager here. So you can see the feature manager is still visible. And I can decide to show more of the feature manager by clicking and dragging, or show a lot less of it by clicking and dragging that kind of separation bar up or down. So, yeah, you get the idea. But we're within the simulation environment here. And all we're going to do, we're going to kind of run from the top of these options or these icons down to the bottom until we've got our simulation set up and we can actually run it. Because there's kind of very few steps that you have to kind of tick off or go through in these static simulations. And they should be relatively easy to kind of remember so that we can set them up in the future. So the first thing that we're going to do, working from top to bottom, is we're going to apply a simulation material to our part itself. So the way that we're going to do that is we're going to right click where it says part 2, because I haven't given my part a name yet. I haven't saved it. So the system's just temporarily naming it part number 2, because it's the second part that I've created in this session of SolidWorks. The first one being the center of gravity example that we did. And then I'm going to edit apply material, or apply edit material, which we've done before, except this time we're in the simulation environment. We're not just in the modeling environment, but we do get access to the same kind of library of materials. So you can see if I just drag that out slightly, the steels are all there, all the other types of metals, everything's there. So I'll just refer to the material that we're going to use for this particular example. So it's a steel again, and it's AISI standard steel, and it's the 1020. So let's find that, AISI 1020. So I picked these just to make them easy to find in the table. There's no real reason that I picked this type of steel over any of the others. It just works with the numbers that we're about to put in. It gives us the kind of stress figures that we need in order to kind of run this tutorial. So then I'm going to apply that material just like we did before. And again, you can see it has things like elastic modulus or Young's modulus. It has things like density, tensile strength, yield strength. So those are the sorts of things that you're looking for in order to be able to run an analysis on what stresses this part might see in use. If you don't have, let me see if I can find something that doesn't have what we need in the woods again, or maybe the rubber. Butyl. Yeah, if you go down into the rubbers section, it has very little information. It only kind of has the density. So if I, for some bizarre reason, wanted to make this thing out of butyl rubber, I couldn't run any form of stress analysis on it at all. Any form of FEA, I couldn't get any readout from it. And the system would tell me that. But if I could go away and research those values, I could then come in and make my own version of the material that I wanted. But generally, the metals in here are very well populated with all the data that you're going to need to run these sorts of analyses on them. So yeah, AISI 1020 is what we want. So press apply. Again, just anecdotally, the appearance changes, and you saw that happen on the part. It's just the default behavior of the system. So I'll click on close because I'm done with the materials catalog now. You can see that that material's been applied to my part. It's listed in little brackets there. So I've kind of ticked off the first step on setting up a simulation. I've applied a material to my part. The next option down, connections. It kind of doesn't apply to us here. So connections come into effect when, let's say, you're dealing with an assembly, or you've modeled a part which is a multi-body part. So again, I've talked all the way through about the fact that SolidWorks can be set to either merge things into a solid block of material, merge different features into a solid block of material, which is what we've done up to this point, or it can leave those separate features as distinct solid bodies, so they're not part of the same block of material. Now, if we'd done that and made our part up from multiple solid bodies, then the connections between those bodies would be something that we'd have to define. But seeing as that doesn't apply to us, we can skip over that step. Down to fixtures. We do have to, for these sorts of static analyses, we have to fix a certain amount of the part in some way and then apply a load to another section of the part. And then the system will go away, simulate that, and give us some information, be it the stress values or the amount of deformation that the part experiences. So we are going to have to set some form of fixture. So we'll right click on fixtures. And given that I said the first time we run this, I'm going to be really sort of crude in the setup of the simulation itself, just to compare and contrast this setup with a slightly more realistic one. So what I'm going to do is I'm going to click on the fixed geometry option. Is there a specific way you want us to do it in our assignment? All I would say about that at this point, because we're kind of just starting simulation, so hopefully as we progress through all these tutorials on simulation, you'll kind of get more of a sense as to what I expect in that area. The level of sort of crudeness that I'm going to show you on this one, I would expect you to be beyond that at least when you come to set up your assignment simulations. But yeah, it will depend. It's a balance between calculation time and trying to be as realistic to the real world situation as is practically possible. And yeah, that is always a balance again. There is no easy answer, I suppose, is the answer. But let me run through these tutorials, and then certainly next week and possibly the week after, and you should get more of a sense as to kind of what's good practice, what isn't, the things to avoid, and the sorts of things that you're going to need to at least be considering. So yeah, what I'm going to do is I'm essentially going to apply what's referred to as a piece of fixed geometry to that end face there, so that eye shape on the end, and the corresponding one round this side, so that end face there. And essentially what I've done by telling the system that those two faces are fixed is, if you want to think about it like this, I've glued them or bonded them permanently to something that is completely immovable. So they're permanently bonded in place. So they're not allowed to move, they're not allowed to rotate. Yeah, they're permanently bonded where they are currently, which in a real world scenario never truly happens. There are no immovable surfaces, or there are no perfect adhesives that don't kind of flex and give and move around. So already we're on to kind of quite an unrealistic setup for our simulation, because ultimately what we're trying to do in this simulation or this exercise is that we're trying to simulate something of how this I-beam might be used in service. And a lot of the time these I-beams are used to hold up block work of some kind above them. So there's an opening of some kind that cannot be supported by columns or walls, and the I-beam itself may see support in a small area on the ends. So the underside of the I-beam in a small area on each end may see some form of support. And then the central section is totally unsupported. And then there's some form of load applied to either the entirety of the top face or maybe to a certain proportion of the top face. So that's ultimately what we're trying to simulate, but we're doing it kind of the bad way first. Quick, but yeah, the flawed way, let's say. So we've glued the ends in position. Click on OK, and you should be seeing those kind of fixed icons. Again, if you're not seeing those green previews that just indicate that you've fixed a piece of geometry, it may be that you've got a filter turned on or off in the show and hide menu there. You can see I'm switching it on and off. The view simulation symbols option switches those on and off. So let's work our way down the menu. We're nearly there to actually run this thing. So the next thing down is external load. So if we right click on there, I think we'll just apply a force. So click on force. And again, because we've been super crude in this initial setup, let's just apply it to the entirety of the top face. So click on the top face there. The system kind of takes that as an input and it selects this option. Create a force which is normal to the face. And again, we know what the word normal means now in SolidWorks. It means at 90 degrees too. So that's the kind of default setup. You can override that and give the system a directional reference. So if I wanted this force to act in kind of a more sort of diagonal motion, I'd have to create some form of sketch or something that had a diagonal line in it that I could then click on. But as soon as I don't have any of that, I'll just set it back to normal again. Now I've got to have a glance across at the PDF to see what I set it on. 100,000 newtons. So there, 100,000 newtons. Make sure the arrows on yours, or the preview of the force arrows, is pointing into the face. If it's not, click on the reverse direction and you can see that would be essentially the face had been glued to something that was pulling it upwards if I set it in that direction. But we want to simulate some sort of mass pushing down on this under the influence of gravity. So we want the arrows pointing towards the face. Then we'll click on OK. And essentially now we've done all the setup steps. We're ready to kind of run this simulation. And the way that we do that is it's this final icon. If you right click on it and go to Mesh and Run. And that kind of folds the final two steps into a single click, because that meshing word there, it's doing something that we're going to investigate later on. But it's essentially chopping this shape up into regular sized elements. But again, we're going to dip into that later on. At this point, we'll just click on Mesh and Run, roll those two kind of processes into a single click, and let the system do its thing. So Mesh and Run, shouldn't take it long to calculate that because it's quite a simple part. And you should be looking at that readout now. Now, initially, that's quite sort of disturbing in terms of what it seems to be showing. It seems to be showing that the I-beam sagged massively in the middle. But the system, by default, exaggerates, or often exaggerates, not always, but if you have a very tiny deflection in your results or your output from a simulation, which we have here, it exaggerates the scale of that to give you more of a sense, you the user viewing it, as to where the part is going to sag or where it's not going to sag. So yeah, initially quite shocking, but I'm fairly sure that this part does not see that level of sag. And the reason that I know that is that in the readout here, in the scale portion of this rainbow plot or this stress plot, it actually tells me what the yield strength of my material is. And it's essentially 3.5 times 10 to the 8. And then up above, this is the range of stresses that my part's going to see under these conditions. And you can see I'm under half of the way there to the yield point. So I'm pretty confident that that amount of sag is not realistic because I'm well within the yield point of the material. And I know it's a steel, and I know the likelihood of seeing that amount of sag would mean I'd be going well beyond the yield point, and the simulation would have probably refused to run. Because when you go beyond the yield point, you're seeing plastic deformation in a metal. So it doesn't spring back after the yield point. It stays deformed by some proportion. And there's a whole different set of mathematics that governs plastic deformations. And these static simulations, these default ones, will give you a little heads up if that is occurring. It will say, you've seen significant deformation. Do you want to switch your solver or your maths model to one which will deal with plastic deformation? Because it's significantly different. If we want to check out how much this does sag in reality, there's a plot which tells us that. So you can see stress is the one that's we're viewing currently, where we can see the amount of stress at any given point within the part. If we double click on displacement, the shape of it doesn't change. It's still exaggerating how much it does sag or displace, but this readout tells us the real story. So this readout is now in millimeters moved, or millimeters of displacement, and you can see even the maximum, which is in the center as you would expect, that's the place which has moved the most. It's 2 mil. So we can assume it's moved vertically on the y-axis around about 2 mil. So yeah, it's not it's not as shocking as it first appeared. So let's go back to the stress one by just double clicking on it and just talk a little bit about the sorts of things that we're seeing. So if we want to, a common thing that you might want to do is you might want to hide all the areas of a design which are seeing very little stress in order to focus on the areas that are under higher stress. And there's a tool to allow you to do that. So if you right click on the stress plot over on the left hand side there and go to ISO clipping, which is that tool there, what we can do here is we get a little black arrow readout on our scale. And essentially all this is doing is hiding a proportion of this scale. So it's hiding all the areas that are seeing low stress. You can see they've all disappeared here. And it's only leaving everything, which in this case is above the arrow. And we can change where that arrow is on the scale. So we can isolate our readout to only show the areas which are above a certain level of stress. And if I put the arrow approximately there on the scale, so I was using this little slider over on the left hand side to vary that scale, we should be able to see that the majority of our issues with this part are the sections which are being sort of abnormally restrained. So these sections that are not allowed to move at all, these end faces, are seeing huge amounts of stress just adjacent to them. So just by them is seeing by far the largest stress over the entire part. And the reason for that is, and this is a good illustration, is the method which we've restrained them is very unrealistic. It will be hard to achieve or nearly impossible to achieve in a sort of experimental setup. And the results that we're seeing are kind of proving that out. The results essentially are a little bit sort of nonsensical. So we need to, so this is just kind of giving you a heads up as to the outputs of these simulations are only as good as the quality of your setup of the simulation itself. And you have to be aware of the sort of shortcomings of whatever setup you've decided on. So what we're going to do is we're going to loop back and we're going to try and improve the kind of setup of this simulation to reflect a little bit more closely the more real world kind of service life of this I-beam. So let's temporarily come out of the results and go back in to the setup section where it says fixed geometry. Let's loop back into the model first and then we'll come back into here. So what we're going to do now, we're going to make a subtle change to the model to allow us to set up our simulation a little bit more realistically. But in order to do that, we have to come out of simulation mode and go back into modeling mode. And the way that you do that is these tabs down at the bottom there. So we're currently in a simulation known as static 1, but we want to go back into the model as if we were just in part modeling mode that we have been in up to this point. So just click on the model tab. The simulation is still retained. It's still there. If you click on it, everything's still there. It's not lost it. It's just drop you back into the modeling interface so you can make changes to the part itself. So what are we going to do? I think what it'd be wise to do is to allow us to restrain this I-beam or support this I-beam over a certain proportion of this lower face. Now, in order to do that, we have to chop this lower face into clickable sections, let's call it that. Or we have to split the face itself. Because currently when I click on that face, the system sees it as one unified large face. There is no way of defining an area over here that I can click on, which is different from the central section. But that's what I want. I essentially want, in my simulation, a stack of blocks underneath, or a small wall which supports this I-beam, let's say for 200 mil inwards. So I want to sort of box off a little section at the end. So the first step in doing that is to create a sketch to define how much of this face I want to kind of designate as the area where this I-beam is going to be supported. So I've got a sketch on the face. That's the first step. So if you click on the face itself, there's two icons that look like sketch icons. It's the lower one of the two. So we want to create a new sketch on the face. The upper one would take me into the sketch that created the I-beam itself. So it's not the upper one, it's that one. Click on that, then I'm in sketcher mode, and all I'm going to do, I'm going to zoom into one end of the I-beam like that. I'm going to get my corner rectangle. I'm going to lock one corner to the left upmost corner of the I-beam, and then the other one to the opposite edge of the I-beam there. And then I want to put a smart dimension on this of, I'm just looking at the reference material again. Where is it? It is, I think it's 200, but I'll just confirm that in a second. I'm sure it was 200. Oh, maybe there's not a screenshot of it. Yes, it is 200. So that, and that essentially represents, if you want to think about this in terms of buildings, it's a stack of concrete blocks. And the final one is 200 long, if you like, and this I-beam is sat on top of them. But I want to support the other end of the I-beam in exactly the same manner. So I'm going to do a mirror of that bit of sketch that I've just created. So mirror entities, do a box select on that rectangle that I've just sketched. Mirror about what? So I click on the mirror about what box, and then select that central plane, which is easier said than done. So I've had to zoom quite a long way into that just to pick that front plane as it is here. And then click on OK, and I should have a mirrored copy of that. Yeah. So I've got one on one end, one on the other end. These are going to be the sections of that face that are supported. So click on OK on that sketch. I'm not currently creating a feature from it. I just want to go and do the same thing, but now on the top face of the I-beam. So I've kind of put my sketch that I'm going to use to block out some areas on the bottom of the I-beam, and now I want to do the same on the top. Because the thought is the load or the force that I'm going to apply, I want to apply it to a specific area of the top face. I don't want to be locked into just applying it to the entire top face. I want to have some ability to direct it to a certain portion of that face. I've still then got the option of applying it to the entire face, but this gives me that second option where I can kind of target it to a specific area. So again, click on the top face this time. Click on that new sketch icon. So it's the sketch icon that's on the kind of lower line. And then this time I'm going to use a center rectangle. Lock the center to the origin point, and then lock one of the corners to the edge of the I-beam, like that. And then the kind of length of this rectangle is going to be a lot longer. So this one's going to be 1.4 meters long. So it's the majority of the center section that I'm going to apply a force to. And then I'll OK that sketch as well. So I've got two sketches currently. Now I need to create the split face feature that uses those sketches to split these two faces into multiple pieces. So that will be a feature. It's in the features tab. And I've made sure, again, just so that I'm not inadvertently clicking on anything before I initiate this split face, I've just hit the escape key a couple of times just to make sure I've not got anything pre-selected. So it's in the curves option in the features toolbar. How long was the last rectangle? 1.4 meters, I think. Yeah, 1400 millimeters. There it is. So, yeah, I haven't got anything selected. I've okayed the two sketches. The two sketches are just sat there in the feature manager waiting for some input. Make sure I've not got anything selected. Go into the features tab at the top there. And the option that we want is a sub option in the curves icon, sort of near the end of the toolbar. Curves. Split line, because we're splitting a face. Split line. There's two things to select here. There's the sketch that we're going to use to do the splitting. So in this case, I'm going to select this one on the top of the I-beam. And then it automatically goes down to the second selection box. And that is just the face or faces that I want to split using that sketch. So in this case, it's just that top face. And then I'll click on OK. And then hopefully what you can see, at least on my readout, it's put these dashed lines, just signifying that that center section now, as far as we're concerned, is clickable. So the center section is a distinct, separate thing to the outside sections, which is kind of what we're trying to achieve. We want to be able to apply fixtures in simulation to a specific area of a face, and we also want to be able to apply loads or forces to a specific area of a face, not just be limited to the entirety of that face. So we've done it on the top. We can do it again on the bottom. So I'll rotate my view around a little bit. So I'm looking at the bottom of the I-beam. Click on curves, split line again. The sketch that we're going to use this time is this bottom sketch. And then the face that we're going to apply it to is this underside of the I-beam. And then click on OK. And it hides those sketches, obviously, because it's created two new features there. Split line 1 and split line 2. And those two features have kind of gobbled up the sketches that went to create them. So the sketches have been filed away inside the feature, and their visibility has been set to hidden as well. So now we're ready to go back into the simulation and kind of refine our simulation setup a little bit. Hopefully make it slightly more realistic. So the way that we're going to do that, we could initiate a new simulation if we wanted to, but a lot of the setup steps, like the material application, things like that, we've already got them in this existing study. So we just kind of need to go in and modify them slightly. So if we click on static 1, down at the bottom there, that static 1 tab, the system quite rightly is kind of alerting us to some problems. So you can see I've got these red X's and I've got these little yellow triangles. It's basically noticed that we've made a significant change to the input geometry, and it's alerting us to the fact that we can't simply run this simulation again. We've got to fix it essentially. We've got to tell it how we now want it set up, given that we've changed the model in some way. So what I'm going to do, I'm going to right click where it says fixed and go in and make a modification in there. So edit definition. I don't want to fix those two end faces because we said that's relatively unrealistic in terms of how this I-beam will kind of see service. So I'm going to right click on that box, click on clear selection, and it will delete all those existing faces. Rotate around underneath and apply it to that 200 mil section on the underside. And it's kind of matching partner over the other side of the I-beam as well. So that's slightly more realistic. There's still a level of sort of unrealistic setup here in that essentially these fixed constraints or these fixtures that use simple fixed geometry are gluing this I-beam in place so that those two faces that we've clicked on, no matter what loading the rest of the I-beam sees, will always remain where they are in 3D space currently, which, again, in the real world, that can never occur. So yeah, but we're accepting that we've improved the realism, or we've improved the accuracy of our simulation from the initial setup. I think what we'll study at the end of this, once we've kind of run to the end, is certain other steps that we could put in place, or certain other types of fixtures that we could use that would kind of improve the realism again. But we've at least made an improvement this time. So click on OK. We've got our fixed areas. Let's go down and edit the force, because the system's kind of shouting at us. So these kind of red icons, if you're unsure as to what it's trying to tell you, you can right click on one of them and go, what's wrong? And it will kind of give you a more wordy description of the issues that it's got. And these are, in this case, related to the changes that we made to the model. So it might contain duplicate or invalid geometry. In our cases, it's invalid geometry because we clicked on a face that is no longer there. That face has become 3 separate faces on the top there. So the original face no longer exists. And the system's quite rightly confused by that. It doesn't understand. So if we right click on that again and go edit definition, it just has one last sort of rant at us, if you like, saying there's something wrong in there, you need to fix it. Okay. And it's actually deleted all the inputs into this box. So the problem was so catastrophic with the model that it couldn't even kind of transpose what it thought we were trying to achieve. It just deleted that face. So now what we're going to do is pick that center section. So we've upgraded our simulation in the sense that we've given ourselves the ability to target our fixtures and loads. No more than that, really. But it is a kind of step up from the initial, which was we could only click on entire faces to do our restraining or our application of our actual force. The magnitude of that force we still want as it was. We still want it acting in a normal direction. We still want it acting in what we are considering down or towards the Earth, if you like. So the direction of gravity. So everything else we can just tick just to accept. And then we'll do a mesh and run again. So right click on where it says mesh. Again, if you want some more detail on what its issue is, why is it put a little yellow icon there with an exclamation mark there, you can click on what's wrong. And in this case, it's going to say the mesh that you previously created is no longer valid because you've made a change to the model. So even though you didn't change the external shape of the model, you made a significant change, and I don't trust that the mesh is up to date. So you're going to have to remesh. But that's okay, because we are going to. So right click, mesh and run. And then we should get our results again. So we dropped into the stress results, which is kind of the default setup. I still have my ISO clipping in effect. So if you remember the point that I left this at before we kind of circled back and made the changes to our model, was I'd used that ISO clipping tool to eliminate bits of this stress plot that were of no real concern to me. So the bits that were under relatively low stress, I'd kind of got rid of from the plot. So the areas that I'm seeing now are everything that's above this arrow. But if I kind of want to change that again, I right click on the stress icon there, go to ISO clipping. I could get rid of the ISO clipping altogether by just dragging the arrow right down to one end of the range. Then I can view the full range of stress values. The takeaway that we want to sort of be aware of by this plot, though, is that the yield strength of our material hasn't been exceeded in any point of our simulation or of our readout here, which is a good thing. And I think I've kind of written that in the PDF there, which is we have a maximum value. I hope they sort of agree with each other. Yeah, they're within a tolerance of each other, I think. So they're around about 2.5 times 10 to the 8 in the units that we're using, newtons per meter squared, in terms of stress. And the yield point of the material, so the point at which it goes into permanently deformed plastic deformation, is 3.5 times 10 to the 8. So we could say with reasonable security that if you were to load this beam up in a similar way to the way that we've set it up, you wouldn't permanently deform the beam. But the next bit of the PDF, so we can pat ourselves on the back. Part does not exceed the material yield point, very good. But often, or almost always, parts are designed to a factor of safety. So I should have put that in little inverted commas. Factor of safety is the key term, or FOS. And that basically means how many times lower than the yield point is the maximum stress within the part. So we are, I could do the maths here, but I can't really be bothered. So let's say the yield point was 4 and we were seeing a maximum stress of 2. So we're only halfway to the yield point in that case. So you could say we had a factor of safety of 2. So that's kind of what factor of safety means. And undoubtedly, depending on what industry you're in, there will be kind of a range of factors of safety that your industry will tend to work with between. And if you're in an industry where making things as light as possible is very, very important, like motorsport, for example, and maybe right at the top of motorsport, Formula One, you'll be working with factors of safety of about 1.1 or 1.2. So you're right on the raggedy edge of the parts not quite surviving. Whereas if you're in an industry such as the one that this I-beam might come from, like the civil engineering and building buildings and things like that, you might have a factor of safety of 8 or even 10 or more. So it's variable depending on the industry and depending on what is important within that industry. Is it important to make the lightest possible part, or is it important to overbuild things to several times beyond the stress that they will see within their life? But this all kind of leads us nicely onto the fact that we can have a factor of safety plot as well. So you don't get it by default when you create a simulation output like this, but you can add it in as an extra plot. And the way that you do that is if you right click on results and go to define factor of safety plot. And then I think for this example, there's various setup options here, but if we just want to see one straight away, you can just click on the green tick. Now, that doesn't look terribly interesting, but let's look at the scale first before we actually look at the readout on the part itself. So the scale is showing us, it's showing us that the minimum factor of safety here, so the areas which are, let's say, most at risk of permanent deformation, are down at sort of 1.4 factor of safety. So that's pretty low, relatively speaking. If we were in the Formula One industry, we'd probably regard that as all excess material that needs trimming away. But let's say we're in an industry that's less obsessed with the ultimate mass of everything and more obsessed with things being safe. But then we've got huge areas of the part that I would argue have got way too little stress in them. They could have material taken away and the part would not flex significantly more. It wouldn't be significantly less safe, particularly. So that's kind of what we can take away from this. The reason I say that is these parts are, what are we looking at? 5 times 10 to the 3 over the top. They've been over engineered by that ratio, 5 times 10 to the 3. Whereas these are getting pretty close to dropping under a factor of safety of 1. So when you go under a factor of safety of 1, those are the parts, those are the sections of a part that are going to permanently deform. So they've gone beyond their yield point. So again, back to the PDF. Often parts are designed with a factor of safety, which is defined as how many times lower than the yield point is the maximum stress within the part. Define a factor of safety plot. We've kind of done that. So we've done these steps. Define factor of safety. We'll put a minimum annotation. So another useful tool that you've got is, as well as being able to see that the minimum factor of safety within a given design is listed at the bottom of the scale there. So it's around about 1.4 for us. If I'm wondering where that is on my part and it's not immediately obvious, we can get a little sort of annotation attached to the area of the part that's seeing the high stress, or that is running at the minimum factor of safety. So let's do that. Let's right click on the factor of safety plot, go to, I believe it's chart options. Yes, minimum factor of safety. There we go. So we get a little annotation. If I can drag that. It's not letting me drag that on my system now. I should be able to drag that out of the way, but it's not. But it's essentially, it's in that area there. It gives me a little heads up as to where it is. And if I make a design change and then come back in, it may have moved to somewhere else. So it's quite a useful little tool. And likewise, if I double click on the stress plot, if I wanted to view the same area but in the stress plot, I would right click and go chart options. Only this time it's not the minimum factor of safety, it's the maximum stress. The two are the same as each other. So the maximum stress that a part sees in any area of the part is going to be the same area as the minimum factor of safety. So maximum stress point, it's there. And it's still not allowing me to drag that. It should allow me to drag that out of the way so I can place it wherever I want. But yeah, you can see the area to which it's attached. It's under there, which is the same area that the factor of safety, that low factor of safety, was kind of drawing my attention to. Now, we're going to use these kind of concepts a lot more in the next tutorial, or the next section of this tutorial. But just as one sort of final little almost thought experiment on this one, if we were to try and improve the sort of the accuracy of the setup of this simulation, some of the things that we might want to think about are that in service, again, in our theoretical sort of service scenario that this I-beam is being installed in, it is undoubtedly sat on a surface here. Now, we're going to regard that surface itself as unmovable, or ground surface. So it can't move itself. But the I-beam is not perfectly bonded to the top of that surface, I would argue. The I-beam is merely being supported from falling to the floor by that surface. So it cannot pass through it. The two surfaces cannot intersect with each other. It will stop gravity's effect of wanting to push the whole I-beam down onto the floor. And that's it. So this I-beam is almost resting on it. Whereas the fixed type of fixture that we've put on there essentially is simulating a perfect bond between the two. They're bonded together. So if this stack of material that the I-beam sat on can't move, then that face of the I-beam also can't move. And that kind of, looking at this area in our stress plot, kind of confirms that, if you know what you're looking for. So the majority of this face that we've permanently bonded into position is under very, very minimal stress. You can see it's down at this end of the stress plot. And that's because it's been what I'd consider perfectly supported by this virtual stack of bricks, or stack of whatever it is, that cannot move. But As soon as it leaves that virtual stack here, there's a huge stress concentration, and it's the highest stress concentration in the entire part. And this is what you see. If you too aggressively or too unrealistically restrain something or your part in a manner which is arguably quite unrealistic in real service life, where your part then leaves that perfect fixture and transitions to being unsupported, which is this section here, you will see huge stress concentrations, which you probably wouldn't see in real service. So if you repeated this experiment but in a lab, you probably wouldn't see that there. So it's drawing our attention to something which is purely caused by our poor setup of the simulation. So that's what you kind of got to be aware of. You can't too aggressively restrain your parts or too aggressively fixture them. You have to kind of think about how they would be held in place in reality in the actual service life that they're going to see. So in order to address that, let's delete that fixture, and let's try and think about some other way of fixturing this thing that is a bit closer to what it's going to see in reality. And I would argue that we need to tell the system that that face there that we've kind of blocked off is allowed to slide, but is not allowed to move in the y direction. So the y direction being vertical as far as we're concerned. So it's not allowed to move vertically, but it is allowed to slide around on its perch, essentially. So that would be a good start, I would argue. So if we right click on fixtures, there are various different types of fixtures other than just fixed. The one that nearest approximates what I've just described is the roller or slider option. So in our version, this would probably be closer to a sliding connection. And you can see from the icon above, it's two faces that are allowed to slide over each other. They're not allowed to pass through each other. So in our case, this virtual face, which is touching our I-beam, will not move, but it is essentially, let's say, made out of Teflon. So it allows the I-beam to slide around on top of it. So let's apply that to that face there and that face there. And then click on OK and have a go at rerunning it and see what happens then. So mesh and run. And undoubtedly what the system will say is there's some form of problem. And the problem's related to the fact that excessive displacements have been calculated. And that's because now we've come into a situation where our I-beam's not adequately restrained. It's not adequately fixtured. So we've stopped it from falling to the floor by defining that sliding face fixture, but it's free to move on X and Z, how it sees fit. And what's happened is as this force gets applied in the center, some slight imbalance has caused this entire I-beam to slide either in Z or X, and the system can't handle that. When it encounters excessive displacements, the maths no longer work that allows it to calculate the stress values. So what we're going to do is cancel. We're going to try and correct that now. So again, you have to put a little bit of thought into how is this part actually going to be used in service. I would argue that there's a vertical face on the end of the part that again has a sliding interface. So there's a vertical face here and there's a matching one on the other side here, so that the I-beam has been slid into a pocket within the building. So there's an upright there that's stopping that end of the I-beam moving in Z. So we can simulate that. So again, fixtures, right click on fixtures, roller slider again. So that face can slide around, but it can't move in Z. So you can see, if you want to know what direction Z is, you look at the little sort of tri-axis readout at the bottom left. So we're gradually cutting down on its degrees of freedom, but arguably in a slightly more realistic manner. So there's only one. It can still slide around on X. So it can still slide kind of side to side. And there are various ways that we could get rid of that degree of freedom. We could chop this side face down. So we could use a split feature command to chop that side face down as well. But I think just to get this simulation running now, because I know there's not going to be huge side forces on this beam, I'm going to make a sacrifice with my simulation accuracy, and I'm going to apply a very sort of inaccurate constraint to that edge and that edge there. So not the face this time, just the edge itself, to say just gently hold the I-beam so that it doesn't move in the X direction. So what I'm going to do, right click on fixtures again. Now there's no easy and quick option for this kind of fixture, so I'm going to have to use advanced. But one of the options in advanced is I can now click on anything. I can click on an edge, I could click on a single point if I wanted, or I could click on a face. I can select any piece of geometry from the part. So in this case, I'm going to click on that edge, click on its neighboring edge over there, do the same thing over the other end, like that edge and that edge. So I've collected the edges I want to apply it to, and all I'm going to do is I'm going to tell these edges they're not allowed to move in X at all. And even though that's unrealistically restraining this thing, for a start, it's applying it to an edge, which is kind of a bit of a no-no. But I know that the sort of forces that are going to be acting on this I-beam along X, which is how we're restraining it here, are going to be minimal or infinitesimally small. They're going to be very insignificant. The majority of the force on this is being applied in the Y direction. It's only slight little imbalances in the calculations that are causing these X and Z direction forces. So I'm reasonably happy to make this concession now. So what I'm going to do is I'm going to tell the system relative to the right plane. So you can see I've got right plane selected there. I do not want you to allow these edges to move normal to that right plane. So that is the option at the bottom there. Normal to plane. Click on the icon and leave it set as 0. So what you're communicating to the system there is it's free to slide around. These edges are free to slide around vertically, and they're free to slide around along the length of the actual I-beam itself, because those two are left unticked. So they're left grayed out like that, unticked. But I want to restrict how it's allowed to move normal to the plane. I want to restrict it to, in this case, 0. It's not allowed to move normal to the plane. And then when we click on OK, then we should be able to mesh and run, and it should not see any excessive displacements. Yeah, it's reasonably happy there. And essentially what we've achieved is a kind of more realistic simulation of, if you have a surface which is resting on another surface and you're loading them, or you're loading the part, which is the upper surface, when the part then leaves that surface and goes into sort of the portion of the part which is supported by its own stiffness, the transition point won't be as harsh. It will be more like the real situation in the real world. So yeah, the thing to take away from that is, don't use the sort of more simplistic methods of restraining your parts if you don't have to. Try and design the fixtures so that you don't see these artificial huge stress levels where the part leaves the fixture. put a little bit more thought into how you're fixturing things, essentially. But this is just a first pass at this. You'll get more kind of experience with this as the tutorials go on, because we're going to do quite a lot more on simulation. How are we doing for part? How are we doing for time? Sorry. Yeah, we're in the last 10 minutes. So what I want to tackle next, it's probably worth saving that one because we may kind of double back and look at that again. So the next and final kind of portion of this sort of introductory week, which we're going to have to now bump into next week's lesson, but that's okay. It's kind of using some of the same tools that we've just looked at with the I-beam. So if we just browse through the PDF that we're going to run through next week. So essentially, again, it's another simple beam design, except this time it gets restrained using, again, for our thought about how this is used in service when it actually gets manufactured, it's restrained by some form of shaft that passes through that hole there, and some form of shaft which passes through that hole. And then there's some form of weight which is suspended, or mass which is suspended from that hole there. So similar, but slightly different. We've got through holes. We've got essentially sort of a cantilevered design. So we do the setup steps just as we've done before. So we're in the simulation. This time we're using a fixture which sort of simulates a hinge, which is fixed in space for these two. In this particular example, we're using a slightly different method of applying a force. So we're defining the direction that gravity is acting in. That's what that big red arrow is. We're defining the acceleration due to gravity, which we've just defined as Earth gravity. And then we've applied a mass to an actual face. So a mass has been applied to that internal face. And then obviously the system takes that mass and the acceleration due to gravity, and it calculates the force that then gets applied to that face. So far, so similar to what we've done. And then we get a readout eventually. So we get a stress plot. So here's the stress plot. On this particular readout, the stress level, or the maximum stress level in the part, has gone beyond the actual yield point of the material. So we didn't see this on our readout, this red arrow. Or maybe we did, but it was right at the bottom. So that essentially shows up when the yield point of your material has been exceeded in your simulation. So it can show you by how far it's been exceeded. If you put the maximum annotation on, it'll show you the worst area that's worst affected by it. And it'll essentially prompt you to then make a change in your part to strengthen the design in that area. So that's what we're going to do. We're going to strengthen the design as simply as we know how, just by thickening up the area where the highest stress is occurring. So that's what's been shown here. And then we rerun it, and then we are below the yield point. So you can see in this particular example, yield is at 2.7, and we're seeing a high stress of around about 1. So that's brilliant. We've cured it. But the last bit that we're going to tackle there is minimize the mass. So even though we've cured it, we've overshot by quite a way. You can see there that we could nudge our way all the way up to just under the yield point. And even though we wouldn't be considering factor of safety there, we could be reasonably confident that the part is not going to yield in service. And then the last bit of that, because everything up to that point is kind of what we've done, is automating that optimization of the design. So this last part here is what's known as a design study. You can see there it says design study 1. And what that allows you to do is you give the system access to the dimensions that govern your part. And the system will go away and rerun that simulation hundreds or thousands of times if you want it to. And it will adjust those dimensions and see what is the optimal design, and then present that back to you with you having to do minimal input. So you just set up the actual design study itself and then just wander off and then come back when the results are done. So that's what we're going to do next week. But yeah, there's no point in starting that right now because it's kind of quite involved. So yeah, we'll drop into that next week. And then we'll go on and do a few other sort of simulation examples. So just before we all sign off, is there anyone that still hasn't got access to simulation? Just so I'm aware of it, at least. So I'm assuming that's a no, which is a good thing. So you've all got some form of simulation running. Just in terms of the people then who are running the virtual desktop, can we just people shout, just say yes if you're running the virtual desktop, just so I've got a sort of sense of that as well. So that's 1, 2, right, okay, because this is going to have a knock-on effect. So yeah, just keep them coming. If you're using it, just type yes. Yeah, so the virtual desktop has got another add-in as well as the simulation that is active on there. So you guys won't have to care about what I'm about to say. But the people who are running it on their local systems who've installed it, I'm going to have to release to you the instructions on how to install SolidCam, which is actually subtly different to SolidWorks Cam, which I think at least one person, they've installed SolidWorks Cam, which is confusingly, that is a subsection of SolidWorks. It comes from the SolidWorks developers. They include it with SolidWorks, but we're going to be using an external plugin called SolidCam. But I'll release the instructions on how to install that, because you can install, I think, a 6-month or maybe 2-month free version of that that will get you that functionality. And we're not going to cover that for at least a few weeks. So don't worry about getting it. Will this work with 2020, 2021? Yeah, it should do. It should do. I know the virtual desktop version of everything is now on 2021, which I wasn't aware of. The version in the labs, I think, the last time I was in there was 1920. But yeah, the virtual desktop version's now 2021. But I believe the virtual desktop version of SolidCam is still back on 2017. But that shouldn't matter either. Because, yeah, even looking forward, if some of us or all of us end up back on campus, then we'll all still have access to the virtual desktop. So as a last case, sort of last ditch, the virtual desktop is running the most modern version of SolidWorks. So if at some point we all need to sort of unify on a unified version of SolidWorks, we'll probably all use the virtual desktop version as sort of a last ditch sort of option. But we're not there yet, so don't worry about that. So yeah, I think I'll sign off and we'll drop back into that next week. So yeah, save the I-beam one at least, I would have said, as we may sort of drop back into that sometime later on. But yeah, I'll see you all next week, and we'll keep going with that. And we'll do a little bit of motion next week as well. So the simulation with moving parts and assemblies. So we'll have a little look at that. Okay, right, I'll see everyone next time.